Hi friends, welcome to our channel. Here, let's look at problem 11, container with most water. This is a daily challenge problem. Actually, this problem, the statement is very short, but it's a very typical problem. Therefore, mastering the logic and coding of this problem is very important in the sense that if you attend some interviewing, right? So here, actually, the main point is to understand the logic, because once you understand the logic, coding is rather straightforward. So let me first say the expectation for this video. So for this video, I hope that I can help you understand two things. The first thing is the logic of the problem, and the second thing is symmetry and some or certain level of abstract reasoning, right? So after this video, I hope that you can try out problem 42 and problem 407. So these three problems, the context are similar, but the techniques to address them are different. Therefore, you can collect them and do some practice. So here, basically, we want to trap as much water as possible. So the water actually determined by the area between the two bars. So if you know the height of the two bars, then the area will be the width, which is the difference of these two, times the height. The height will be the shorter one between the two ends, right? That's the main point. So if you look at example 1, so the return is 49. So basically you choose the first one, you choose the second one, and then you choose this one, right? So then the in between, so there are, so this is the 3, this is the 6, this 8. The length is 7. So 7 times 7 is 49, right? So before we explain the logic, so we also quickly look at the constraints. So here the length can be as long as 10 to the power 5. So 10 to the power 5 is a decent large number. Therefore, we need to think of time complexity of the algorithm. So here the lower bound 2 is nothing but for consistency. Here the height, so we just need to pay attention to this one, greater than or equal to 0. So in other words, all non-negative, right? So with that said, we are ready to do the coding. As we mentioned that we use two-pointer sliding window method. Actually, the two-pointer sliding window method can take on different representations and address different problems. I guess for most of the coding videos, they didn't actually explain the rationale or the validity of the technique. So here, let me quickly explain the logic. So what we want actually is to maximize the area, right? So we know the area will be something like this. So it will be the width, let's call it dx width, then times the mean of the height, right? The short, let me mean of the two sides. You're going to choose, right? So once we realize this point, so we can first targeting to maximize dx. How do we maximize this dx? For sure, we put the first one in one end, and then the other one in the other end, right? So you can put two pointers L and R to the two end. So this for sure the dx is maximized, but the two corresponding height might be not that good, right? So because you want to multiply by the height at L and height and R, so the minimum of those, right? So, but if you understand the goal to maximize the area, so once you maximize this one, so you get this information, then what you can do is this. So you compare, let me just use capital H for to represent this height, right? For convenience of writing. So first, if HL is less than HR, right? So in this case, I would increment L by 1. So this is the logic. So why this is the right case. So in other words, symmetrically, um, um, if the right head is smaller, so we are going to shrink the right side. So why we do this? The reason is that you can use contradiction, right? Contradiction to argue. So if at this assumption you shrink R, so you shrink R by 1, then the area will be something like this. It originally is R minus L times the mean of HL and HR, right? So this is the previous. So now if you shrink R, so then the area will be something like this, R minus L minus 1. So because R changed to be R minus 1, then minus L. Then you do this, L and HR minus 1. But because we are taking mean, so this is less than or equal to R minus L, R minus 1 minus L times HL, right? So because we are assuming HL is less than HR, or we consider in this one. So this is exactly, here, R minus L times HL. And therefore, if you shrink R, so actually it's less than or it will not increase, right? Because it's less than or equal to the previous area given here. Because here originally they are R minus L, here you are R minus L. That's why, so we need to increase L. This is the one thing, right? So let me restate. So if you found, so one set is smaller, you need to, for example, here L is smaller, I need to increase L by 1. Same thing, if R is smaller, so I'm going to shrink R by 1. So this is the right logic, with the hope that potentially you can increase, right? So because if you if you increase L in this situation, right, then the area will be something like this, R minus L minus 1, because L is increased. But then you times mean of HL plus 1 and HR. So this is possibly larger than this one, right? Because this one might be larger, right? So that's the logic. So then you want to argue. So what if HL equals HR? So in this case, I would say you can do either L plus 1 or you can do R minus 1. So why this is the right? This is due to symmetry. The reason is that the left and the right is actually relevant. You can see that side is L and this side is right. But if you fix the left side, I still see it's right, then the other side will be left, right? Therefore, this is actually the same, right? So in other words, so if they are different and one is larger, so we are going to increase the smaller side. If they are the same, so we can do from either side. So this will be the full logic. Up to now, I hope that I at least point out to you the two. One is the logic of the problem, and the other is the symmetry and a certain level of abstract reasoning. So with that said, we can work on the code. So as I mentioned before, let me use capital H just to save some typing. So I want to initialize a result variable and then the two pointers. So not this, right? So L is pointing at the beginning and R pointing at the, so let me point to the length of the height minus 1. And then we can do the two pointers. So L is less than R. So we don't consider L equals R. So if L equals R, so it has no positive result. So right. So then first we can update the result to be the max of the previous result and the mean of height L and height R, right, times the width, that is R minus L. So that's the same. So now we are going to do comparisons, right? So first, if height L is less than or equal to R, right? So this actually contains the equal case because as I mentioned, for the equal case, you can do either side. But here, let's absorb it here, right? Because L is smaller, so we can increase L side. Otherwise, it's corresponding to L side is larger, so we are going to decrement R by 1, right? So each time when we enter this while loop, we are going to compute and update the result. So this way, we always get the maximum result. So here, actually, I want to say, so if HL is less than HR, so here we should do increment by L. The reason we do not do this set, you can think that, oh, we ignore a lot of areas that is smaller than or smaller or equal than the current one, right? So that's the where we save time. So finally, you can return the result. With that said, you can do some test. Yeah, it passes the 2 test cases. So here, I'm not going to do some printing. So you can try to digest this code. This code is actually very short, but the thought process behind is crucial. So now let's look at the generic case. Yeah, it passes the generic case. So with that said, I would say that's basically about it for this problem. Again, let me mention that I'll encourage you to try out problem 42 or 407, right? So if you find that those videos are helpful, welcome to thumbs up on the video or share with your friends so we can practice together. Thank you for watching.